In March 1989, the electrical grid in Quebec experienced a total collapse. In a matter of seconds, 6 million people lost power. That 1989 blackout was a minor event compared to the Carrington Event of 1859. During that storm, the physical forces were so intense, they literally set telegraph offices on fire. The sun operates on cycles, which makes another storm of that magnitude an eventual certainty. The danger lies in how those exact same forces will interact with today's highly fragile, hyper-connected power grid. Over the last century, we have hardwired the globe. This total reliance on electricity makes modern society exponentially more exposed to solar weather than humanity was in 1859. The primary engine of this threat is the Coronal Mass Ejection, or CME. These are massive eruptions on the sun's surface that launch billion-ton clouds of highly charged plasma into the solar system. When targeted at Earth, these plasma clouds strike our protective magnetosphere, which violently compresses the planet's magnetic field. Space weather is not always a uniform planetary wave. It often manifests as localized substorms and mid-latitude positive bays. These phenomena create highly concentrated, rapidly fluctuating magnetic spikes over specific geographic regions. These localized spikes are what terrify grid operators. Solar activity can behave like unpredictable lightning strikes, catching a specific city or region completely off guard. This diagram shows a cross-section of the Earth. When the geomagnetic field fluctuates rapidly, it induces low-frequency quasi-DC electric fields within the crust of the planet. This creates horizontal electrical currents moving directly through the rock. Because rock is a poor conductor, these crustal currents seek the path of least resistance. They divert out of the Earth and travel straight up into the metal pylons of our high-voltage transmission lines. These geomagnetically induced currents, or GICs, physically infiltrate the grid through neutral ground connections. They travel up from the Earth into the transformer, split through the windings, and flow out onto the phase conductors. The grid's design contains a fatal contradiction. The grounding connections engineered to protect hardware from terrestrial lightning are the very entry points that invite catastrophic space weather inside. This diagram shows the internal physical mechanism of failure. Quasi-DC current pushes the transformer into half-cycle saturation. Magnetic flux escapes the core entirely, bleeding into surrounding components. This creates localized hotspots that melt internal insulation and cause the transformer oil to violently off-gas. The second symptom affects grid stability. The saturated transformer becomes a massive sink for reactive power, absorbing VARs at an extreme rate that drags down the voltage of the entire connected network. Finally, the saturated core generates heavy, even-order harmonic currents. These distorted signals trick the grid's protective relays into falsely tripping active power lines offline. A solar storm does not smash grid infrastructure with physical force. It forces transformers to consume themselves from the inside out, while simultaneously blinding the safety systems designed to prevent a collapse. This environment extends straight into orbit. Satellites caught in the storm suffer severe internal electrostatic charging, leading to sudden hardware failures in space. Back in the atmosphere, passengers flying at high altitudes receive radiation doses typical for nuclear workers. Meanwhile, scrambled ionospheric currents sever the GPS timing signals that synchronize global data. A regional blackout initiates the cascade. The superstorm's ultimate threat is the simultaneous, uncoordinated collapse of global telecommunications, navigation, and aviation networks. Our first line of defense is purely observational. We rely on a small fleet of forecasting satellites parked 1 million miles away at the L1 Lagrange point to measure incoming plasma. Because of their position, these satellites only provide grid operators with a window of 15 to 45 minutes before a storm physically impacts the Earth. This schematic illustrates neutral blocking devices, or NBDs, installed in the neutral ground path. Massive capacitors physically block quasi-DC GIC from the transformer, allowing alternating current to flow. However, this dam forces current to aggressively surge into neighboring, unprotected substations. To prevent a normal lightning strike from destroying the equipment, NBDs must also be equipped with massive spark gaps or metal oxide varistors that safely bypass sudden voltage spikes. Defending the modern world relies on a meticulously balanced, network-wide engineering strategy. Success depends on managing the flow of the entire planet's crustal currents at once. We cannot stop the sun from unleashing another Carrington event, but through rigorous physics and precise grid engineering, we can ensure that when the plasma hits, it results in a controlled defense rather than a global dark age.